Hi, my name is Greg Mead. I'm a faculty member at Santa Fe College in Gainesville, Florida. I'm putting together a series of videos on geologic time and how to use the principles of geologic time to tell how old things are, both in relative terms and in absolute terms. This is the second of several videos. I will have links to the other videos below this one. But this particular video is going to discuss radioactive decay. Radiometric dating is how we generally figure out the absolute age of geologic features, in other words, the age in years. And because radiometric dating depends on radioactivity, I put together this webpage, and I'll have a link to that as well. And the purpose of this particular video is to show you how radioactive decay, the three most common types of radioactive decay occur, and how to calculate what new isotopes form as a result of that. And so you can take a look at this on your own, but the three types of radioactive decay that occur that most commonly, the first is known as alpha particle decay, and then we also have beta particle decay and electron capture. And in alpha particle decay, and alpha is the first letter of the Greek alphabet, in alpha particle decay, 2 protons and 2 neutrons are ejected from the nucleus, and that combination of 2 protons and 2 neutrons is known as an alpha particle. It is represented like this. That's the Greek letter alpha. And because there are 2 protons and 2 neutrons, an alpha particle is a kind of nucleus. And in fact, it's the nucleus of a typical helium atom. And because it's a nucleus, we represent the atomic number, which is the number of protons, and we represent the atomic mass number, or the atomic mass, which is the number of protons and neutrons, by numbers. The atomic number goes down here, and since there are 2 protons, we put a 2 there. Because there are 2 neutrons and 2 protons in an alpha particle, that's a total of 4 particles, and we put that in the upper left. The only correct way to write this is with the 2 down at the bottom and the 4 up at the top on the left side. If you write it any other way, it is not correct. This is not a time to be creative. You can't put numbers wherever you want. You can't put, for instance, you can't put a 4 here and a 2 here, or a 4 here and a 2 there, or anything else like that. None of that would be correct. The only correct way to do it is to do it this way. And the reason that I am being so emphatic about this, you might guess, is because I have seen all these errors. So make sure that when you write out an alpha particle, you write it out with the atomic number down in the bottom left and the atomic mass number in the upper left. And that's shown right here. A beta particle happens when a neutron explodes in the nucleus. And a neutron can be thought of as a combination of a proton and an electron. And so a neutron has 0 electric charge, so it has no proton. It is not a proton, so its atomic number is 0. It is 1 nuclear particle, and so its atomic mass number is 1. And when it explodes in the nucleus, it turns into a proton and an electron. And so a proton is here, an electron is here. A proton has 1 positive charge, it's a proton, so it's got an atomic number of 1. And it is a nuclear particle, so it has an atomic mass number of 1. An electron is very, very light, and for our purposes, we can consider it to have a 0 mass. And so its atomic mass number is 0, but its electric charge is opposite that of a proton, so we can consider it to have an atomic number of -1. And you'll notice that if you think of this as an equation, 1 equals 1 plus 0, 0 equals 1 plus -1. And so this is how we're going to be doing the math. When this happens in a nucleus, the explosion of the neutron into a proton and an electron is extremely energetic, and the electron is ejected at high speed from the nucleus. And it is known, when it is a high-speed electron like this ejected from the nucleus, it's known as a beta particle, and this is the second letter of the Greek alphabet, the letter beta, which eventually turned into, of course, our letter B, just like alpha eventually turned into A. And so we represent it like this. Notice that the atomic mass number and the atomic number are the same as for an electron, because it is in fact an electron, but we're calling it a beta particle because it's a high-speed electron that leaves the nucleus. Electron capture, as it says right here, is exactly the opposite of beta particle capture, beta particle decay. In electron capture, an electron around the nucleus is drawn into the nucleus, and instead of being ejected from the nucleus, this electron joins with a neutron within the electron joins with a proton in the nucleus to become a neutron. So it's exactly the opposite of what we looked at before. We get an electron and a proton turning into a neutron. And remember that the electron has a -1 atomic number. The proton has a +1 atomic number. The proton has a +1 atomic mass number. The electron has a 0 atomic mass number. And that results in a neutron with a atomic mass number of 1, but a charge and therefore an atomic number of 0. And so in beta particle decay, when beta particle decay occurs, the number of neutrons in the nucleus drops by 1, but the number of protons in the nucleus increases by 1. Exactly the opposite occurs with electron capture. When electron capture occurs and an electron joins with a proton, the number of protons in the nucleus drops by 1, and the number of neutrons in the nucleus increases by 1. So in both cases, the atomic mass number of the isotope stays the same, because you replace a proton with a neutron or vice versa, but the number of protons changes by 1. It either goes up by 1 in beta decay, or it goes down by 1 in electron capture. So let's take a look at some examples of how this happens and how you can figure out what is going on. Now, I've got some examples right here, and I'm going to invite you to read these on your own. This is alpha particle decay. This is beta particle decay. And here is electron capture. But I'm just going to show you some examples of how to figure this out. And I've picked up off the net, I picked up a periodic table of the elements, and there are literally dozens of these that you can find. And we can pick an element at random, and I'm going to do that by finding chromium. Chromium has, let's look at these numbers. Chromium has an atomic number of 24. This number, and you probably can't read it, 51.996, that is the atomic weight. That is the average of all the different isotopes of chromium in nature. You will not use that at all during these problems. And so if we take an isotope of chromium and with an atomic number of 24, and let me make sure you can see that. I'm going to turn this slightly so you can see that. And I will, in fact, I'll just make this larger. If we can make up a isotope of chromium, and I'm going to just pretend that we have an isotope of chromium with an atomic mass number of 54. And we can pick anything. It doesn't even have to be a real isotope. If we have chromium 54 with 24 protons, and if you subtract 24 from 54, you get 30 neutrons, or just an atomic mass number of 54, then if you have alpha particle decay, when alpha particle decay occurs, you are basically subtracting one alpha particle from the nucleus. And so we could write it like this. So we're subtracting 4 from 54, we're subtracting 2 from 24, and this is going to result, and you could put an equal sign there instead of an arrow, with how many? If you take 4 neutrons and protons from a total of 54, of course you get 50, and I'll write it up here. And if you have 24 protons and you remove 2 of them, I think you can probably do this math without a calculator, you're going to have 22 protons. And notice that because of the fact that we have changed the number of protons, we no longer have chromium. This is a characteristic of every type of radioactive decay. We change what the element is. And so we would have to look here, there's 24, 23, 22. This would give us titanium. And so we have a new isotope. And so this arrow would point out to that. There are other ways of doing this. The way that I like to do it, and I'm weird, so you can do it this way or not if you prefer. I like to think of the chromium atom in alpha particle decay as exploding, leaving us with an alpha particle. And what gets left over? Well, again, we are taking 4 away from 54, so we're going to get 50. We're taking 2 away from 24, so we're getting 22. And again, that is titanium. Okay. The other way you can do it, and you can do it this way, you can do it that way, whichever way works best for your brain, do it that way. The other way you can look at it is like this. Chromium during alpha particle decay breaks up into an alpha particle and something else. The alpha particle has an atomic mass number of 4, an atomic number of 2. So what do you have to add to 4 to get to 54? Obviously 50. What do you have to add to 2 to get to 24? 22. And again, that winds up with titanium. So this is the process that we use to come up with alpha particle decay. It doesn't matter what isotope you start with, you can do exactly the same thing with any isotope. Okay, once again, my camera's battery ran out, so I'm starting over again. I think you saw how we used alpha decay to get the results of chromium decay. We can do the same thing with any other element. And if, again, I take an element at random. We've got PD, which is palladium 46, is the number of protons. So PD 46. And again, we can pick any isotope. The atomic mass number here, or the atomic weight, is 106.42. So it's very likely there's a 106 or a 108 or a 107 as one of the isotopes. Let's pick 108 because it'll be fairly easy to calculate. If we have 108 as the atomic mass number of this isotope, oops, and I will move this, actually I'll move this over a little bit so you can see it better. Make sure that you can see that okay. There you can. Okay, we can do the same thing we did last time. We can say if we eject an alpha particle from palladium 106, it's going to have an atomic number of 2, an atomic mass number of 4, and that's going to leave us 108 minus 4 is, of course, oops, sorry, that should be an arrow there, or an equals sign. You can use either one. That will leave us with 104 total neutrons and protons in the nucleus. And if we take 46 and subtract 2, that of course is going to be 44. And notice again that we have changed the element. 44 gives us Ru, which is ruthenium, as our new isotope. Again, we can do this in a number of different ways. We can do it the way that I like doing it. Say that it breaks up into an alpha particle, and then what's left over after we take away 4? 104. What's left after we take away 2 from 46? 44. And again, that leaves us with ruthenium. Or we can say 108, palladium 108 turns into an alpha particle. And, well, what do we have to add to 4 to get to 108? Obviously 104. What do we have to add to 46 to get to 2? What do we have to add to 2 to get to 46? 44. And again, that's ruthenium. So try doing this with different isotopes. Take one of these at random, and you will see that you will always wind up 2 to the left of wherever you started with, because you're removing 2 protons, and your atomic mass number will always drop by a total of 4. Okay, so that is alpha particle decay. What about beta particle decay? In beta particle decay, we have a situation where a neutron blows up into a proton. And so we can, again, look at our periodic table. And we can pick at random. And again, we can pick anything. Let's pick Re. Re is rhenium, I think. Re has an atomic mass, an atomic number, excuse me, number of protons of 75. So we would write Re with a 75 down there. And as you get to larger and larger elements, you typically have more and more neutrons. And so let's say we have, let's see, double that would be 150, maybe 160 for the number of the atomic mass number, the number of neutrons plus protons. And so if we subtract an alpha particle from the nucleus, sorry, we are now subtracting a beta particle from the nucleus. And a beta particle has an atomic mass number of 0 and an atomic number of -1. then again, if we think of that arrow as an equal sign, what's 160 minus 0? I think we can do that without a calculator. That is 160. 75 minus negative 1, when we subtract a negative, that's the same as adding a positive. That's going to give us 76. And if we look here at 76, 76 is osmium. Okay. Now, we can do this in a number of different ways. We can say that we know that this breaks up into a beta particle. And why does it break up into a beta particle? Because a neutron blows up into a beta particle and turns into, the electron leaves, and that leaves a proton behind. So the number of protons, what happens? It goes up by 1, 76. Because we're simply replacing a neutron with a proton, we're not changing the number of the atomic mass number, and so that remains at 160. And again, if we look at an atomic number of 76, that's going to give us osmium. And then, just like we did last time, we can also say 160 and 70, 160, 75, rhenium, and that turns into a beta particle. And what do you have to add to 0 to get to 160? Obviously, you have to add 160. What do you have to add to minus 1 to get to 75? You have to add 76. And again, that's osmium. Okay? And we can, again, do this for any isotope. We could erase this, and erase this, and erase this, and erase this, and this, and this. And we could pick cadmium, Cd. 48. Let's say there's an atomic number, or an atomic mass number of 100, just to make the math easier. 100 minus 0 is 100. 48 minus negative 1 is 49. If we look at our atomic table, 49 is In, which is indium. Same thing here, 100, 48, Cd. We take a neutron in cadmium and turn it into a proton, so the number of protons rises by 1, 49. Because we're just turning a neutron into a proton, the number of neutrons and protons collectively stay the same. And again, we get the same answer. And finally, if we start with cadmium 100, and we look at this, we say, what do we have to add to 0 to get to 100? 100. What do we have to add to minus 1 to get to 48? 49. And again, we get the same number. And you can do this for any element on the periodic table. It's the same process no matter what you use. Our last example is a little different because something is now coming into the nucleus. And in this case, we have we have electron capture, which is right down here. And so we're pulling in an electron and turning a proton into a neutron. So again, if we look at our periodic table and grab something at random, oh, that's osmium, we already dealt with that. Gold, hey, we got gold, okay. 79, gold has 79 protons. Say it's got 190 neutrons and protons, just for the sake of argument. We could pick a real number or not. Now, what we're doing is we're adding an electron and turning a proton in the nucleus into a neutron. If we take this strictly mathematical, 190 plus 0 is 190. 79 plus -1 is 78. And we would turn gold into platinum, which is still a valuable metal. Or we could do it like this, 190, 79 AU, and we could say we're going to take an electron and draw them together into the nucleus. Let me make sure you can still see that. Yes, you can. And we can turn a proton into a neutron, so the number of protons will drop by 1 down to 78. The number of the atomic mass number, the number of protons plus neutrons, because we're just changing a proton into a neutron, that stays the same. And again, that's going to give us with platinum. So these are the 3 types of radioactive decay you were likely to see. And when you do the homework assignments that I've assigned for geologic time, you'll see this. You'll see this kind of thing on the exams I give as well. And certainly if you are taking a geology class from somebody else in some other school, you're very likely to see the same kind of thing. So make sure you know how to deal with alpha decay, beta decay, and electron capture. All right? Good luck. I hope you enjoyed this.